In this video, we'll take a look at the solutions in detail to this Unit 1 review on vectors and their properties for the MCV4U vectors and calculus course. And so in the first one, we're asked which of the following is a scalar quantity. We have the choices of velocity, weight, acceleration, force, and price. Now, price would be the only scalar here because all of these other things have a magnitude and a direction. Even weight, your weight is a force of attraction between you, or whatever the object is, and the heavenly body that you're standing on, whether it's the Earth or the Moon or Mars or wherever. And so it's a force just like D. So E is the the price is the only scalar quantity here. For number 2, you're given two vectors and asked which of these are true of them. And so notice that they are the same length, but they're going in exactly the opposite direction, so they would be called opposite vectors. So D would be the correct answer here. For number 3, we're given these two vectors and asked to find P dot Q. Now, P dot Q or Q dot P, doesn't matter, the order would be exactly the same thing. And so we multiply the x component -2 by the x component 5, so -2 times 5, plus 6 times -2, that's the y's, plus 1 times 4 for the z. So that's -10, that's -12, and then plus 4, and that works out to -18. For number 4, we're given 2 points and asked to find the vector's components between them, vector AB. So you take the coordinates at point B, where the head of the vector is, or the tip of the vector is, and subtract the tail's coordinates from that. So we would go 4 minus -2, and then 1 minus 5 for the y. And so that works out to 6 -4, and so that's why A is the correct answer for number 4. For number 5, KU has the same direction to vector U, and under which condition? And the scalar K, see, KU is a scalar multiple of U. It's some multiple larger or smaller. If the scalar is positive, then they're in the same direction. Now, like for example, 2U or 10U or something, that would be a vector in the same direction but longer. B is almost the same answer as D. But notice there's an equal to sign. You can't have K being 0, because if you multiply a vector by 0, you get the 0 vector, which has no length. And something that has no length cannot have a direction. So K can't be 0. So that's why B is not correct, but D would be the only correct answer here. For number 6, you're asked which of the following is a correct version of the dot product formula for solved or rearranged for cos theta. So here's my work down here. This is the definition of the dot product. It's the magnitude of the two vectors multiplied times the cos of the angle between them. And so if you take that, and what I did was I rearranged, I put this on the left and the A dot B on the right. So I just switch sides. And then I want to solve for cos theta, rearrange for cos theta. So I divide out the magnitude of A, magnitude of B. And so that's what I've done here. So the reason for that, so that those divide out, and then on the left side I just have cos theta, and that's what it would equal, A dot B over the product of the two magnitudes. So that's the answer A up here, so that's why that is the correct one. For number 7, the cross product of two vectors yields a vector perpendicular to both the original vectors. So let's say this is vector A and vector B. This is what A cross B would look like. And it could be longer or shorter, but that's the direction it would have. And it would be drawn so that it's perpendicular to vector B, and also that it's perpendicular to vector A. So that's what the diagram would look like. That's what you get for a cross product. That's the end of multiple choice, so on to the second part here. Now, for the test in my class, please note that 5 of the communication marks will be assessing your overall achievement in communication, an overall mark through part 2. For number 1 here, you asked to list a pair of equal and a pair of opposite vectors for this parallelogram. Now, if we're told it's a parallelogram, the opposite sides are the same length, so we know the vectors would be the same length. Now, a pair of equal vectors, well, this AD and BC would be a pair of equal vectors. They are the same length and going in the same direction, so they have to be equal vectors. A pair of opposites are, for example, AB and CD. AB goes towards the right, CD goes towards the left. They're the same length, but they're opposite directions, so they would be opposites. Now, please don't say that AB equals CD. They are equal in length, but they're not equal in direction, so they are opposite vectors. Now, if you ignore the arrows, another possible solution here is you could say that AB, and if instead you said DC, they would be equal vectors because they're both going towards the right. A pair of opposites, you could say AD and CB are opposites if you don't use the actual arrows in the diagram. For number 2 here, you're asked what would vector AD minus AB be, and then illustrate it on the diagram. Now, so what I would do is I would create a vector equation or expression. Equation is a better word, using the triangle law here involving vectors AD and AB. And so if you look here, if we start at A, the vector AD plus DB. Now I said DB, not the vector that's illustrated here. It's actually its opposite. So AD plus DB, and that's what's written right here, and that would equal vector AB because it goes from the beginning of the first vector to the end of the last vector. And the reason I wrote that one is because it involves AD and AB. Now I want to know what AD minus AB is, so I'm going to rearrange this. I'm going to bring the AB over to the left, and so it would be minus AB, and I'll take this DB over to the right, so it would be negative DB on the right. And so AD minus AB is equal to the negative of DB. Now another way to write the negative of DB, and that would be an acceptable answer, that's okay. You could write that as BD, because that negative just means the opposite of DB. And so that would be BD. And so that's why I'm illustrating that on the graph. That would be vector BD. For number 3, you're asked to illustrate the vector negative 2, 3, 1. I'm calling it vector W on this graph, and make it look three-dimensional. Now, on these axes, this is the positive x-axis. It kind of looks like it comes out of the page. The y-axis goes horizontal, positive y is to the right. Z-axis goes vertical, positive is up. And so if I want to plot the point negative 2, 3, 1, I would start at the origin, and I'm not going the positive x, I'm going the negative x. So I would go 2 back here, and then 3 in the y. So after going 2 back here, I would go 3 in the direction of the y, positive y, and then the 1 means 1 up. So I go negative 2, 3, 1 up. That point right there would be the point negative 2, 3, 1. The vector negative 2, 3, 1 would be the vector that goes from the origin to that point. Now to make it look three-dimensional, I draw a box around this so you can see the sides and it makes it look three-dimensional. So that's what the diagram would look like. For number 4, we're given this diagram and asked to draw to scale 2a plus 3b minus 3c. Now, to scale means when you make copies of vectors or multiples, you make sure that they're the proper length. So this is vector A, and I want to start with 2a. So I've actually shown here drawing 2 vector a's. So from here to here would be 2a. Plus 3b. So now I need to add 3 of these. So at the end of the 2a, I would draw 3 vector b's, or a 3b. And then minus 3c. Well, this is vector c here. Minus 3c is the same as adding negative 3c. So notice that vector c goes up in this direction, so negative c would go down in the exact opposite direction. So there's 1, 2, 3 of them. So that's a negative 3c. So the vector 2a plus 3b minus 3c would go from the beginning of the 2a vector to the end of the negative 3c vector. So it would be this red vector right here. For number 5, we're asked to prove algebraically using Cartesian vectors in 3 space, so 3 components, that this is true. So to prove it, you wouldn't take specific numbers for vectors a, b, and c. You couldn't say that a is 1, 2, negative 5, and b is 0, 3, 6, or something like that, because that would only prove it for those specific vectors. The reason I'm going to call a the vector a1, a2, a3, and say that a1, a2, a3 could be any real numbers, and the same with b and same with c, is because if I do that, then that's covering all possible cases. Since a1, a2, a3, b1, b2, b3, and c's components as well could be any real numbers, as long as I show algebraically that the two sides are the same, then that's proving it for all possible cases. And while it may look trivial, that a plus b plus c is equal to a plus b first plus c, this is how you would prove it mathematically. It's not even like a quarter law that they normally say prove beyond a shadow of a doubt. In mathematics, we have to prove things absolutely, that there's absolutely no room for error. It's not just probably correct. Okay, so this is how you would prove this. So I'll start with the left side, the a plus in brackets b plus c, and substitute in my vectors. So that's a, and that's b and c there in place of the b and c vector. And the brackets means I am supposed to add b and c first. So I would add the x component to the x component. So b1 plus c1 is the x component, comma. b2 plus c2 is the y component, comma. And the z component would be 3 plus c3. And then after I've added that, I'm supposed to add a to that vector. So I'd add a1 to b1 plus c1, so that would be a1 plus b1 plus c1, comma. And then for the y's, a2 added to b2 plus c2 would be this. And then a3 plus b3 plus c3 is a z component. So that's what the left side works out to be. Now we would do the same thing for the right, and of course we should get the same thing. So that's the right side, so we substitute in my vectors, and these brackets means add a and b first, and so that's what this would be, and then we add that to c. And so, for example, a1 plus b1, the x component, plus c1 is a1 plus b1 plus c1 for the new x component. Same with y and z. And notice that this is exactly what you have up here. And so since the left and right sides are the same, then this would be true. You always should have a concluding statement like this at the end of your proof. On to number 6. From the diagram below, we're asked to write each of the following vectors as a linear combination of some other vectors, either multiples or a linear combination. And the first one here, we're given vector HD. Well, HD would be the vector that goes up along here. We're asked to write it in terms of m. This is vector m here. So this would be 1, 2, 3, 4 vector m's. They're going in the same direction. So we would say HD equals 4m. For B, we're asked to write EC. And EC would be the vector that goes from E across to C here. We're asked to write it in terms of vector P. Now, notice that P is parallel to that, but going in the opposite direction. Again, there'd be 4 of them. So we would say, write EC equals negative 4P. For C, we're asked to write BE, and that would be this red vector right here, in terms of M and P. And so to go from B to E, triangle law, we could go up here, and that's 2 M's. And then across here would be, in terms of P, that would be 4 P's. So 1, 2, 3, 4 P's. So BE is 2M plus 4P. And the last one, FA, would be this vector right here. We're asked to write it in terms of M and R. So to go from F to A, I would go down here, and notice that that's 2 negative m's, so this would be negative 2m here on the right side, and then along here would be 4 r's. So FA would be negative 2m plus 4r. For number 7, we're given 2 vectors, a and g, and asked to find or determine 5a minus 3g. So 5a minus 3g would be 5 times this vector minus 3 times this vector. So multiplying the 5 in, 5 times negative 5 is negative 25, 5 times 2 is 10. Multiplying the 3 in here, 3 times 3 is 9, and 3 times negative 1 is negative 3. Notice I just multiplied the 3 in, so there's still a negative here. There's actually 2 ways to do this. That's what the other solution is about over here. And so we would subtract these. Negative 25 minus 9 would be negative 34, and 10 take away negative 3 is the same as 10 plus 3, so that's 13. Now, instead, if you multiply the negative 3 in, negative 3 times 3 would be negative 9, and negative 3 times negative 1 would be positive 3. If you multiply the negative 3 in, then this would now be a plus between the 2 vectors. And so when we add them, of course, you get exactly the same thing. So 2 different ways to do that. Number 8, you're asked to determine the axis or plane, and be specific about where each of the following pairs of points are located. And so at A here, we're given 0, negative 2, 3, and 0, 1, 8. Now, if the x coordinate is 0, that means that you're not going along this line at all. So negative 2, 3 means I would go left 2 on the y-axis, so negative 2 on the y-axis, and then up 3. And you're actually on the YZ plane, because think of like the vertical plane, like almost like a wall. Then that's where you would be. Same for the 0, 1, 8 point. So I don't go forward or back. The 1 means I would go 1 here and then 8 up, and so I'm on that YZ plane. So whenever you have 2 points or more, I suppose, and the x coordinate is 0, but y and z are both non-zero, then it would be on the plane of the non-zero points. So it would be the YZ plane. For B here, we're given the points 4, 0, 0 and negative 11, 0, 0. So 4, 0, 0, I will go 4 in this direction, and then nothing right or left and nothing up or down. So I'm on the x-axis. And same with the negative 11, 0, 0, we'll go back there 11, and then nothing right or left, nothing up or down. So you're still on the x-axis. So if two of the coordinates are 0 and one's non-zero, then you're on the axis of the non-zero one, which of course would be the x-axis here. For number 9, a plane takes off with an airspeed of 300 kilometers per hour at an angle of 21 degrees to the horizontal. So you're actually traveling 300 kilometers per hour on that flight path. And you're asked how long will it take the plane to cover a horizontal distance of 5 kilometers. So the horizontal or speed or ground speed can be found by calculating the horizontal component of this vector. And so to find the horizontal component, the magnitude of that, it would be 300 times the cos of 21 degrees. So that's 280 kilometers per hour. So although the plane is flying 300 along that path, it's actually only passing over the ground at a speed of 280 kilometers per hour. Now, velocity is distance over time. We want time. So we rearrange this for t. Time is distance over velocity. The distance is 5 kilometers. The velocity is 280. And if you divide that, you get 0.01786, and that would be hours. Now, if somebody asked you this, like a pilot, for example, you probably wouldn't tell them, well, it's 0.01786 hours, because that's not, well, how long is that? A more reasonable amount of time would be to put that in minutes or seconds. So I'm going to convert it to seconds here. There's 3,600 seconds in an hour. 60 seconds in every one of the 60 minutes. 60 times 60 is 3,600. So if you multiply that to those together, you get 64. So it's just over a minute. So it's about 64 seconds it would take for that plane to travel 5 kilometers horizontally along the ground. For number 10 here, you had a friend, and the original diagram is the one in black here, drew this diagram to try to find the sum a plus b plus c. And you're supposed to write a note about what they did wrong and then fix it. So notice that, okay, here's A, and then there's the vector B, but notice they actually have them placed tip to tip instead of tip to tail. Okay, so that's my note here. The friend placed the B vector incorrectly. She placed the A and B vectors tip to tip instead of tip to tail. So to do it correctly, I'm going to start with the vector A still. So I'm going to take this vector B and place it here instead. So there's the tip to tail. The end or tip of A is where the tail of B starts. So there's the vector B there. And then this is supposed to be my vector C here. So there's a vector C along there. So the A plus B plus C vector goes from the beginning of the A vector to the end of the C vector where the tip is. For number 11, you're asked to determine the angle between these vectors, m and n. And if you go back to the, it was the last or second last multiple choice question, we solved for the cos theta in the dot product. Cos theta is the dot product divided by the product of the two magnitudes. So we need the dot product of these two vectors, so we will go negative 4 times 3 plus 2 times negative 2. So that's negative 12 minus 4 is negative 16. We also need the magnitudes of the two vectors. So the magnitude of vector m would be the root of negative 4 squared plus 2 squared. So that's 16 plus 4 would be the root of 20. I won't bother finding what decimal it is. I don't really need to, although you could. For n, the length of vector n would be the root of 3 squared plus negative 2 squared. So that's 9, and 4 is 13. So the length of vector n is the root of 13. So filling all these in, the dot product is negative 16, and we have the product of root 20 and root 13 in the bottom. Now, in order to punch this in your calculator a little bit more conveniently, you might want to multiply this. 20 times 13 is 260, so that's the same as the root of 260 in the denominator. So dividing negative 16 by the root of 260, we get negative 0.9923. So to get the angle, we take the inverse cos of that, and we get 173 degrees. So that's the angle between these two vectors. They're almost opposites. If that was 180, they'd be opposites, but not quite. So that's the angle between the two of them. Moving over to the last page here. Number 12 here, a plane is traveling at 310 kilometers per hour on a heading of east 12 degrees north. So this is the 310 kilometers per hour, and it's going not quite east, but it's going 12 degrees towards the north. So that's that vector right there. And there's a 25 kilometer per hour wind blowing at north 35 degrees east, so towards north 35 degrees east. So placing the plane vector and the wind vector tip to tail, there's the wind vector of 25 kilometers per hour. And so its direction is, that line there is north, and it's 35 degrees toward the east. So that's 35 degrees right in there. Now, in order to find the sum of the two vectors, that's the plane's velocity. That would be the vector from A to C here. And so we need to calculate, I'm going to use the cosine law here, not components. We need to calculate this angle in here. So if this is 12 degrees right here, this line here is an east-west line, so completely parallel with this one here. And so that's the Z pattern. Remember, this is 12 degrees, this would be 12 degrees up here. And so the whole angle here would be 12, plus this would be 90, because that's north, that's west, plus another 35. So the angle between the two vectors, if we add 12, 90, and 35, we get 137 degrees. So that's that whole angle from here to here between those two vectors. And so in using the cosine law, the length of vector v would be squared, would be 310 squared plus 25 squared minus 2 times 310 times 25 times the cos of 137. And so if we evaluate all that, now be careful when you do this. I didn't show all the steps here, but the cosine of any angle between 90 and 180 is negative. And so when you multiply negative 2 by 310 by 25 by that negative value, that'll actually end up being a positive value that will be adding to whatever 25 squared and 310 squared add to. So be careful of that when you do that calculation. So that's what that all works out to be. We take the square root, we get 328.7 kilometers per hour. Notice that it's a little bit faster than the airspeed because the wind's actually sort of blowing it along and helping it a bit. Now we need a direction. Well, I would find the angle A here, this little skinny angle in here, to use to find a direction. So I'll use the sine law for that. The sine of angle A over the 25 side would equal the sine of this 137 degrees over this length of the side we just found, the 328.7. So the sine, isolating for sine A would equal 25 times the sine of 137 divided by the 328.7. So if we evaluate this, you get 0.05187. Take the inverse sine of it, and that works out to be approximately 3 degrees. And that is a small angle, so that's 3 degrees. So the direction of that, if we add that 3 and the 12 here, the whole angle from here up to here is 15 degrees. So the plane's velocity is the 328.7 kilometers per hour at a direction of east 15 degrees towards the north. For number 13, we're asked to find the projection of M on P. And so this is the one of the two projection formulas. M dot P over P dot P times the vector P. We're projecting M onto P. So to find the dot product, we go 8 times negative 5 plus negative 3 times 1. So that's negative 40, and negative 3 is negative 43. P dot P would be negative 5 squared plus 1 squared. So negative 5 times negative 5 plus 1 times 1. And so that's 25 plus 1 is 26 in the denominator, times the negative 5, 1 vector. So if we multiply this fraction by negative 5, negative 43 times negative 5 is 215, and that has a denominator of 1, so 1 times 26 is still 26 in the denominator. 1 times negative 3 over 46 would be negative 3 over negative 43 over 26. And so that's the projection of M onto P. Last question, number 14, we're asked to find the area of the triangle formed by these 3 points, C, D, and E. Now, the area of a parallelogram formed by two particular vectors, so let's say that vector and this vector here, so CD and CE would be the parallelogram that goes right out here. I'm going off the screen here a little bit, I know I am, but that whole parallelogram. If you take the cross product, the magnitude of the cross product of those two vectors, it's the area of that entire parallelogram. Now, we only want the triangle, so we would take half of that magnitude. So, and that's just the definition of what the magnitude of the cross product is. It's the area of the parallelogram that those two vectors enclose. So, to find the components of these two vectors, remember we subtract coordinates. So for CD, we will go 8 take away 2, negative 2 take away 4, and 3 take away 7. That's what I've done here, so we get 6, negative 4. For CE, we would go 0 minus 2, 9 minus 4, and negative 2 minus 7. And so that's negative 2, 5, negative 9. So that's the two vectors that we have to take the cross product of. So this is the system I normally use. So I'll write down negative 6, negative 4, 6, negative 6, right there. And then 5, negative 9, negative 2, 5, right there. And so to calculate the cross product, I go negative 6 times negative 9, which is 54, minus this product. So minus negative 20 is the same as plus 20. Negative 4 times negative 2 is that 8 right there, minus negative 54, so plus 54. And then 6 times 5 is 30, and then minus this product, so minus 12. So 54 and 20 add to 74, 8 and 54 add to 62, and 30 minus 12 is 18. So that's the vector right there. Now we're taking the magnitude of it and then half of that. So the magnitude would be the root of 74 squared plus 62 squared plus 18 squared. That's the root of 9644, and then we divide it by 2, and we get just under 50. So it's about 49.1 units squared. That would be the area of that triangle. And that's the end of the video.